Hi, everybody. This is Dr. Nigro with a Chemistry Notes screencast. This screencast is part of my series that focuses on Unit 3. In that unit, we're working on ionic naming, balancing, and stoichiometry. This particular screencast is going to be one of three that I'm going to do that's going to focus on the last portion of the unit, which is stoichiometry. Now, stoichiometry it's a vital skill. I mean, we have to be able to do stoichiometric calculations. These calculations are prevalent throughout the rest of the year in chemistry, and the word alone seems to be enough to strike fear into students' hearts. I don't really understand why. I mean, stoichiometry, it's a fun word to say, and it's not really any different than mole conversions, which we've already covered. So if you just follow the same type problem solving that you did with mole conversions, you're going to be all set. It's no different. And as a matter of fact, it's going to use some of those skills. It's just going to apply it to a chemical reaction versus a single compound, like we saw in unit conversions. All right, or mole conversions rather. All right, so let me rephrase that again. All right, so these are basically conversion problems within a chemical reaction. All right. So prior to this screencast, we talked about balancing chemical reactions, and that is a vital thing to do prior to stoichiometry. So you're going to hear me say quite a bit, make sure your reaction is balanced. So if you need some assistance with the balancing aspect, please go watch that screencast or come talk to me, because if you can't balance or you balance incorrectly, then your stoichiometry problems have the chance to be incorrect. So we like to make sure the balancing is correct first. All right, so what is the most important aspect of a chemical reaction for stoichiometry? It's this right here, the mole ratio. And that's exactly what it sounds like. It's a ratio among I didn't leave myself enough room. Components in a chemical reaction. So we're going to use a ratio in the mole between our chemical components to move from one chemical entity to another within a reaction. Okay. All right. So what does that really mean? Well, I have a reaction here. I have C3H8 gas plus oxygen gas forms CO2 plus H2O, both in the gas phase. All right. This is called a combustion reaction, and we're going to deal with types of reactions in our next unit. All right, but you can see that this reaction is already balanced. I have 3 carbons on the reactant side, balanced by 3 on the product side. 8 hydrogens on the reactant side, balanced by 8 on the product side. And then 10 oxygens on the reactant side, balanced by 6 in the CO2. And then 4 more in the H2O, so 10 on that product side. So we can use the compounds themselves to talk about ratios to one another. All right. So let's say we're just talking about single particles. All right. So what that would mean is that if I have one molecule of C3H8 gas, all right, then I'm going to be able to react that with 5 molecules of O2 gas. And what's that's going to do for products is it's going to allow me to produce 3 molecules of CO2 gas and 4 molecules of H2O gas. All right. So that's what the coefficients tell us, right? It's like the amount of the ingredient that we need for our particular recipe. So it's the amount of reactants that we need for a full reaction to produce a particular amount of products, which is all dictated by the balanced chemical equation and the law of conservation of mass. So I can talk about it in terms of molecules. All right. I could also scale that up because we know that molecules aren't particularly useful. All right. And if I take my one molecule and multiply that by Avogadro's number, that becomes 6.02 times 10 to the 23rd molecules, which is also known as 1 mole of C3H8 gas. All right. By the same token, I can do the same thing to my 5 molecules of O2. I can multiply that by Avogadro's number, and I'm going to end up with 5 moles of O2 gas. All right. All right, again, I can repeat, take my 3 molecules, multiply it by Avogadro's number, and then I'm going to have 3 moles worth of CO2 gas. And then I end with my 4 molecules. All right, I'm going to multiply that by Avogadro's number, and I have 4 moles of H2O. All right, so because Avogadro's number is the same for all chemical entities, there's 6.02 times 10 to the 23rd particles within a mole of anything. That's where I want to move between my substances. I could do it in the molecule, but we're not going to be working in molecules very often because we tend to measure things in grams, right? So we're going to want to be in the mole versus the molecule, all right? So this really lets me look at some ratios, right? All right, so for every 1 mole of C3H8, I also need 3 moles of O2. All right, well, what if I scale that up? What if instead I have 2 moles of C3H8, how many moles of O2 do I need? And the answer will be 6, right? So that's a ratio, right? For every 1 mole of C3H8, I need 3 moles of O2, and I can scale that up or scale that down, right? I can do the same thing for a product, right? I can say, all right, if I have 1 mole of C3H8, then I can produce 4 moles of H2O. Well, again, I can scale that up. Let's say instead I have 3 moles of C3H8. Well, then I'm going to produce 12 moles of H2O. All right. And the key here is it's the ratio that you can build. So you use the coefficient with the mole and the chemical entity, and you can set these ratio ups amongst any of the components. It can be a reactant versus a reactant, a product versus a reactant, or a product versus a product. It does not matter as long as you're using the coefficients for the balanced equation and you are using the units so that you can cancel what you're trying to get rid of, just like a mole conversion. All right. So the problems that we're going to be working here are going to be unit cancellation problems, just like we saw with our mole conversions. All right. We're going to use the unit that we've been given, put it in the bottom of our conversion factor so they'll cancel, and put the unit that we're trying to go to in the top. All right. So the one we want to get rid of in the bottom, the we want to get to in the top. All right, so when working problems with reactions and using this method, there are a couple steps we need to follow. All right, now some of them are going to seem familiar because we're going to find that balancing and stoichiometry go hand in hand. All right, so the first thing we have to do, we have to make sure that our formulas are correct and that our reaction is balanced. All right, so again, if you need to refresher on balancing, please go back and check out that screencast. All right, underneath your balanced reaction, you're going to write down what the given value is with its unit. This is going to be what you have. And I tend to circle what I have. All right. And then I'm also going to look for the unit that I've been asked for the answer. So this is what you want. And I tend to underline this part of the problem. So I know that the circle is always what I'm starting with and the underline is what I'm trying to find. It just helps me keep organized within my reaction. All right. Next, you're going to write out a plan. All right. And we are going to try this for the beginning, at least until we get the hang of it. Having an idea of the steps that you're going to need to take to get from what you've been given to what you're looking for is going to be important. It gives you a pathway to follow. All right. Once we have that plan, we need to determine what conversion factors or ratios we're going to need. All right. So remember, there are a couple things that we've been working on. We know that 1 mole of any substance is equal to Avogadro's number in particles. So that's one conversion that we know. All right. We also know that 1 mole of any substance is equal to its molar mass in grams. So that's another conversion factor we could use. And now we're going to use what's called the mole ratio as a way to move between substances, where we have the mole that we've been given versus the mole that we're going to using those coefficients. All right, we're going to set up our conversion factor so that that unit that you want to cancel is on the bottom of your conversion factor, and that the unit that you want to find or get to or achieve, whatever you want to say here, is on the top of your conversion factor. All right, now this is very important. All right, I'm going to be looking for this on your tests and your quizzes. Your unit must include these things: the units, so you need the number, you need the unit, and we need the chemical formula. All right, so it's not going to be good enough to just write the number anymore. All right. It's not going to be good enough to just write the number and its unit. You have to have all three of these pieces because we're going to be moving between substances within the reaction. So not everything is going to be for the same chemical entity. So you absolutely have to now include the chemical formula as part of that unit, that number that goes in the conversion factor. All right. Okay, so with everything, it's always best to just practice. So we're going to do this in 3 different screencasts. The first one is going to deal with moving from moles of one substance to moles of another substance within a chemical reaction. So we call this a one-step stoichiometry problem. I'm just going to use the stoic right there. So these are going to be the simplest ones that we are going to see. All right, so what we're going to be doing is we're going to be moving from moles of A to moles of B, or moles of B to moles of A. And to do this, we're going to need a conversion factor called the mole ratio. All right. And depending on what we're trying to convert, the unit on the bottom needs to get canceled. The unit on the top is what we're aiming for. All right. So let's look at what we've got here for a reaction. Solid lead reacts with aqueous hydrochloric acid to produce solid lead 2 chloride and hydrogen gas. All right. So the first thing we're going to do is write the balanced chemical equation. All right. So solid lead, whoops, is PbS. And then we have aqueous hydrochloric acid, and it gave us the formula. So HCl, for aqueous, forms solid lead 2 chloride, and then we have the formula PbCl2 solid plus hydrogen gas. All right, now hydrogen is one of our 7 diatomic elements, so because it's alone, it needs to be H2. All right, now we've written the equation. We need to make sure it is balanced. All right, so it looks like the only elements unbalanced right now are hydrogen and chlorine. So I have 2 of each on the product side, but only 1 of each on the reactant side. So if I put a 2 in front of my HCl, all right, then I'm going to have a balanced equation. Now I'm going to, it's not really cheating, but because I'm on my iPad, I can copy this because I want to show you what I mean by writing things underneath the reaction. I am going to shrink it down though so that I have a little bit more room. All right, so now the question: how many moles of HCl are needed to react with 0.36 moles of lead solid completely? All right, so here's what we have been given: 0.36 moles of lead. So I'm going to put that here. All right, and here is what we are asked for. Whoops, what happened? All right, so we're asked to find moles of HCl. So we're converting from lead to HCl. So as soon as you see that you are moving from one chemical substance to another, you have to have a mole ratio step in your problem. All right, now because we're starting with moles, it's relatively straightforward. All right, so our plan is going to be 0.36 moles of lead to an unknown amount in moles of HCl, and we're going to need a mole ratio step, and that's all. It is a one-step problem. All right, so there's our plan. Now we start with what we have been given: 0.36 moles of lead, and here's our conversion factor. All right, so remember, we're going to put what we're trying to get rid of in the bottom, all right, and we're going to put where we're going up top. And this is where the plan can be helpful. All right, have moles of lead to start with. I'm trying to find moles of HCl. All right, now to fill in the numbers in front, I go look at the balanced chemical equation. And according to the equation, for every 1 mole of lead, I need 2 moles of HCl. And that's coming from those coefficients. All right, so that's going to let me cancel the moles of lead. I'm going to multiply 0.36 by 2. And for every 0.36 moles of lead, I'm going to need 0.72 moles of HCl. All right. All right, let's try another one. Again, I'm going to put my reaction down here. Whoops, but I'm going to shrink it. Whoops, sorry. You know, I'm going to copy my shrunken one too. That might make things easier later. There we go. All right. So if you produce 1.25 moles of hydrogen gas, how many moles of HCl must have reacted? All right. So here's what's given, moles of hydrogen gas. And here's what we're looking for. All right. So we have 1.25 moles of H2, and we're trying to determine moles of HCl. All right, so this is a moles to moles conversion. So that's going to be a mole ratio step, and that's the only step I need. So again, one step. All right. Oh, I forgot to put this. Oh, I'm sorry. So we should have put 1.25 moles under the H2 and then a question mark and moles under the HCl. So this time we're converting to here. All right, again, one step. All right, so 1.25 moles of hydrogen gas. Conversion factor, this unit's going to go on the bottom. Moles of H2. I'm trying to find moles of HCl, so that goes up top. Then I go look at my balanced reaction, and it tells me for every mole of H2 produced, I need to react 2 moles of HCl. All right, again, that's going to let me cancel the moles of H2 and leaves me with moles of HCl. So once I do that multiplication, 2.50 moles of HCl are going to be needed to produce 1.25 moles of H2 gas. Okay? All right, one more. Well, I guess two more technically. I'll put my reaction down again. All right, you have 0.567 moles of lead. That's what we're given. How many moles of HCl do you need to react? All right, so we've got 0.567 moles of lead, and we're asked to find moles of HCl. So we're going to be converting from one reactant to the other. So 0.567 moles of lead, and we're asked to find moles of HCl. So we're going to need, again, a mole ratio step, and it'll be a a one step calculation. So 0.567 moles of lead. All right, now we know this needs to go on the bottom. So moles of lead in the bottom, we're going to moles of HCl. So that's up top. Now we go look at our reaction. For every 1 mole of lead, we need 2 moles of HCl. So when we do our calculation, we find that we need 1.13 moles of HCl to react with the 0.567 moles of lead. All right. So last one. All right. If you produce 2.85 moles of hydrogen gas, how many moles of PbCl2 were also produced? All right. So this time we've got 2.85 moles of hydrogen gas, and we're asked for moles of PbCl2. All right, so this is a product to product conversion, but still one step, right? 2.85 moles of hydrogen gas. We're trying to convert that into moles of PbCl2. So moles to moles is a mole ratio step. So we again start with what we've been given, 2.85 moles of hydrogen gas. Our conversion factor is going to put moles of H2 on the bottom and moles of PbCl2 up top. And we look at the reaction, and it's a 1-to-1, which means that for every 2.85 moles of H2 produced, 2.85 moles of PbCl2 will also be produced. Okay? So you can see that these one-step problems aren't conceptually that difficult. You just need to have a balanced reaction, and you have to understand how to set up that conversion factor. Just remember, when you set up a conversion factor, whatever's in the bottom should be the unit you are trying to cancel, the unit that you were given. Whatever is up top should be the unit that you are trying to reach. Okay. And if you keep that in mind, you should be able to set these up, and then as you practice, it will become easier and easier. Okay. All right. So make sure you come back. I'm going to have another screencast that's going to look at what to do if instead you need to move to mass or from mass within a chemical reaction.